beats. This video is going to be on the topic of terminology for sequences. So this is going to be some vocabulary that we're going to use to describe the behavior of sequences, and once we can get a decent understanding of what this vocabulary is, then we're going to combine it to form a very nice theorem. So let's first talk about terminology. Okay, we're going to go one by one through these things. We say that the sequence a sub k is an increasing sequence if a sub k plus 1 is larger than a sub k for all k. So what that's saying is that the next term in the sequence is always larger than the previous term. For instance, example of this to get the idea across, strictly increasing sequence. What if we had 2, 4, 6, 8, dot, dot, dot. So in other words, that is all the even numbered natural numbers, and each next term is bigger than the previous term. So A2 is bigger than A1, 4 is bigger than 2, A3 is bigger than A2, 6 is bigger than 4, and so on and so on. So that's strictly increasing. Now, what if we said it's non-decreasing? How does that differ from increasing? Well, we say that the sequence a sub k is non-decreasing if each next term in the sequence is larger than, and here's the difference, or equal to the previous term. And that's for all index k. The difference between increasing and non-decreasing is when you're increasing, the next term always has to be larger than the previous term, whereas when you're non-decreasing, the next term could be equal to the previous term but can never be smaller. So, as an example, just take the same kind of example we looked at in the previous one, but then write 2, 2, 4, 4, 6, 6, etc. Then each term is always bigger than or equal to the previous term in the sequence. So the difference being you can be equal to the previous term in non-decreasing, just can't be smaller, whereas increasing has always got to be bigger than the next term. On the contrary, what if you're decreasing? So if you're decreasing, then you have a sequence a sub k in which each next term is smaller than the previous term. So a sub k plus 1 always smaller than a sub k. For example, what if we took the sequence 5, 3, 1, negative 1, 3, negative 3, whoopsies, dot, dot, dot. So what's happening? Each term that you get, the next one in the sequence, is smaller than the previous term. Hence, it's a decreasing sequence. Keep going with this. You might guess what's next. Non-increasing. And based on what we said before, you might be able to guess what this is saying, and that is you have a sequence a sub k, it's not increasing, then each next term in the sequence is smaller than or equal to the previous term. So as an example, let's just consider the sequence. We had 0, 0, then negative 2, negative 2, then negative 4, negative 4, dot, dot, dot. And so here, each next term is either equal to or smaller than the previous term. Again, it's very similar to decreasing, except in decreasing, each next term has to be strictly smaller than the previous term. So we got increasing, non-decreasing that are similar. Then we got decreasing and non-increasing that are similar. So far, we got a few more to talk about here. We say that a sequence a sub k is monotonic, one tonic, if it is either not increasing or not decreasing. So it never changes its direction in terms of getting bigger or smaller, but it can be equal to in successive terms. So it basically kind of moves in one direction, but it can be equal to. So the example we just saw above, that is a monotonic sequence. Or go back to the non-decreasing example, 2, 2, 4, 4, 6, 6, and so on. This one right here is also monotonic. Monotonic. You may be wondering, what about if you're increasing? Would that be monotonic? And the answer is yes. Increasing or decreasing sequences are also monotonic because they're simultaneously, respectively, non-decreasing or non-increasing. Things we were about to say, they're not monotonic, they go up and down, that kind of thing. So monotonic is good, as we're going to see. And then one more thing that's going to be a very nice thing combined with monotonic is that these concepts of being bounded. So let's say we got a sequence A sub k. We say it is bounded below if there is some real number called little m here, so that the sequence terms always are bigger than or equal to that number m. So for instance, if I had the set of natural numbers 1, 2, 3, 4, ... that is a sequence that is bounded below. Why? Because we know here a sub k is k. That's the explicit formula for the terms, and that's always bigger than or equal to 1 for all k. Hence that 1 there, that's your little m, that's your lower bound, as we would say. And so this sequence is bounded below. And then on the contrary, sequence a sub k is bounded above if there is some real number m, so that the sequence always smaller than or equal to that number m, the big M here for bounded above, for all the index k. Here is just all the terms in the sequence can't be larger than some number. If that's the case, you have this upper bound, as we say, and the sequence is bounded above. For instance, what if we just considered the sequence a sub k, where a sub k is the arctan of k? Then we know that this is smaller than or equal to, and technically smaller than, pi over 2. Hence, that's your big M. This sequence never gets bigger than pi over 2, hence it's less than or equal to pi over 2, and it is bounded above. Now, if a sequence is both bounded above and bounded below, it's got to be both, then we say the sequence is bounded. So it has lower bounds and upper bounds. And that's a good thing for sequences because we know it can't get bigger than some number. We know it can't get smaller than some number. And it ends up being a nice behavior for sequences in general, as we're going to see in a theorem coming in a future video here very shortly. Now, having said all that vocabulary, we would like to look at a couple examples. So given some sequences, using all this vocabulary and terminology we just discussed, can we describe its behavior? Let's take a look at this first one here, the sequence 2 to the k plus 1 times 3 to the negative k. Let's just get a feel on how this is behaving by looking at the terms in the sequence. So if k is 1, we're going to get 2 squared, and then, of course, times 3 to the negative k is divided by 3 to the k, so over 3 to the 1. When k is 2, we're going to get 2 cubed over 3 squared. Then when k is 3, we're going to get 2 to the 4 over 3 cubed, so on and so on and so on. And then just to write these terms out by evaluating the operations, we get a 4/3, we get a 8/9, we get a 16 over 27, and so on. So we look at this sequence and say, well, how are these terms behaving? Of course, we could use all our calculus concepts of what it means to increase, decrease, how we're going to get a horizontal asymptotes that are upper or lower bounds, this kind of thing. But just, investigating it intuitively is usually enough. And so let's take a look at the values here. Notice the very first term is 4/3. That's bigger than 1. And then the next term is 8/9. That's 0.8 repeating. And then 16/27. Well, geez, that's getting closer to a half. In fact, because the denominator has a base that is bigger than the numerator, this thing is eventually going to go to 0. So in fact, we could write limit k goes to infinity of 2 to the k plus 1 times 3 to the negative k here is 0. And because it starts at 4/3 and decreases the whole time, it has an upper bound as well. We could say the big M here is 4/3 and little m is 0. Hence, this function is bounded above and is bounded below. So, sequence here is bounded above and below. Now, notice that the terms strictly decrease. So because of that, then it's not increasing, and hence this function is decreasing. And when I say function, I mean the explicit formula for the sequential function. And because it's decreasing, it's not increasing like we said, it's also monotonic. So this is a pretty nice sequence. Okay, now having said that, let's look at another example. Consider this example. The sequence -1 quantity to the k times k divided by k plus 1. Again, let's just write it out, get a feel by how it's behaving here. Okay, when k is 1, then we have -1 to the 1, that's negative, and then times 1, so we can get -1 on top, and on the bottom we're going to get 2, so -1/2 is the first term. When k is 2, -1 squared is +1, then times the 2 on top, over 2 plus 1, 3. How about when k is 3? It's going to be negative again, -1 cubed, and then times that 3, so a -3 on top, over 3 plus 1 is 4. Continuing this pattern, next term would be +4/5. And you start seeing the pattern here, right? The next one would be -5/6, ... so on and so on. This is a sequence that we're going to eventually refer to as alternating because it's switching signs successively between the terms. But for now, we never actually mention that terminology, so we won't necessarily use it. Instead, we're just looking at, okay, what are the terms doing in general based on the vocabulary we just looked at? Do the terms as values have an upper bound or lower bound? That's the question. Well, notice, if you looked at the magnitude of the terms, right? So take the absolute value of each term and then look at that. Well, eventually that's going to go to 1. And in fact, if you did the same thing, the lower bound would be 1/2. So just consider the magnitude of -1 to the k times k over k plus 1 here. That's just k over k plus 1 because we don't consider the negative signs. Hence, if k is 1, you're at 1/2, and as k goes to infinity, you go to 1. So k is 1, you get 1 over 1 plus 1, which is 1/2. And as k goes to infinity, not x, k goes to infinity, we get that k over k plus 1 goes to 1. And then it's just switching signs in between. So we see the magnitudes are growing from the very smallest term to infinity, but because it's alternating in signs, switching signs on each term, then we could say something as follows, and that is that this function is bounded below. Okay, what's it bounded below by? What are all the terms bigger than or equal to then, and that is, shouldn't little m here be -1? As k goes to infinity, this thing, the sequence that's alternating, is going to eventually oscillate between numbers that are really close to 1 and -1. And for that same reason, this sequence is also bounded above by big M, let's say, is 1. And so, therefore, it's bounded above and it's bounded below. And, therefore, it is bounded. Now, think about it. Because it's changing signs between successive terms, it cannot be monotonic. Because it's negative, then it's positive, then it's negative, then it's positive, it's negative, then it's positive. So the terms are getting bigger, then they get smaller, and they get bigger, then they get smaller. That does not satisfy any of the terminology we use to describe what it means to be monotonic. So that's all we can say. It's a bounded sequence, and technically it's alternating as well, but for now we'll just say it's bounded. So it's important to kind of dissect the behavior of these sequences, because eventually, if we can just quickly identify the behavior of something, maybe it's really hard to take the limit of something like that. Then if we combine that with some other few little facts that we're assuming to be true, then we can instantly conclude whether the sequence converges or not. And so we're going to get in that in the next video. And so that's the end of this video. I know it's not the most exciting video, but this terminology is important, and not only just saying the words, but understand how they mathematically are taking place in each sequence. It's important. Vocabulary is important in mathematics and in general. Anyways, that's it. Stay tuned for the next one so you can learn more about sequences, and eventually we'll add stuff up. All right then.